Today we continue our study on differential calculus. In particular, we first study this type of limit. Uh, Consider this formula which we have been using for a while without proof. Sin x over x when x approaches 0, this converges and the limit is 1. However, if you look at the numerator here, the limit of sin x when x approaches 0 is 0. And the limit of x when x approaches 0 is of course 0. So sin x over x when x approaches 0 becomes something like 0 over 0. So which is of course undefined. Nevertheless, it converges and has this limit 1. So consider more general case where we would like to calculate a limit of a function which can be expressed as this fx over g of x for some functions f and g, and if x approaches some value a, let's say, it may or may not converge. So we consider this case where the limit of f of x is 0 and the limit of g of x is also 0. So in this case, it will be the limit of this ratio will be something like 0 over 0, just like sine x over x. And this has a form called an indeterminate form. Net form. Because 0 over 0 is undetermined. More generally, we might have cases like f of x may diverge to infinity or negative infinity. At the same time, g of x also diverges. So in this case, we have something like infinity, positive or negative infinity over positive or negative infinity. So, let's consider only positive infinity for simplicity. Infinities are not numbers. They are not ordinary numbers. So you cannot just reduce this to 1. You cannot do this. This may or may not converge to some constant value or some finite value. But we need some way to tell whether this converges or not. If it converges, then we want to find the limit. Okay, so this case is also called indeterminate form. Okay. Now the next theorem gives a way to calculate the limit of indeterminate forms, and that is called L'Hopital's rule. L'Hopital, it's a French name. L'Hopital's rule. So let f and g be differentiable functions. Differentiable on an open interval, let's say between a and b. And we impose the following conditions. First, we consider only right limits. Okay, so x approaches a from the right, and this limit is equal to f of x g of x. Again, we take the right limit, and they are both 0. Okay, and second, for all x in the interval between a and b, g prime, so the derivative of g, is not 0. And 3, the right limit a plus 0, the right limit of f prime of x over g prime of x, so the derivatives of f and g. And if we take this ratio, this exists. Okay, so again, let's say we have f and g such that their right limits are 0. And for all x within the domain, the derivative of g is not 0. And the ratio of f prime and g prime has a limit, the right limit. Okay, then the limit, this right limit of f of x over g of x exists. And that limit is given by the limit of the ratio between their derivatives, f prime over g prime. Okay, so this means since we are assuming that g prime of x is non-zero for all of x in the domain, so this limit, the latter limit, can be computed. And furthermore, we can replace this first condition, this first condition, by instead of 0, it can be plus minus infinity. This can be the limit of f is positive infinity and limit of g can be negative infinity and so on. So all combinations, positive positive, positive negative, negative positive, negative negative, all combinations can be considered. So even if these are true, then we still have this result. So this right limit exists, and this right limit is given by the right limit of the ratio of f prime and g prime. And of course, the same result holds if we replace these right limits with left limits. And if both right limits and the left limit exist, then we can say the limit exists. So in this way, we can calculate, we may be able to calculate the limits of indeterminate forms. Well, we don't give the proof of this L'Hopital's rule at present, but later we'll give it. But we just first study how we can use this rule. And here is a simple corollary of this L'Hopital's rule, which we call L'Hopital's rule number 2. So here's another L'Hopital's rule. Number 2. Again, f and g are differentiable functions. On an open interval I. And we have the following conditions. So limit of by the way, this interval must contain the point A. Okay, so the limit of f of x when x approaches A is the same as the limit of g of x when x approaches A, which are both 0. And second, for all x in the interval, except for the point A, we should have g prime of x is not equal to 0. And 3, the limit of f prime over g prime when x approaches a exists. Then the limit of f over g when x approaches a exists, and the limit is equal to f prime over g prime. Okay, so even if this limit is an indeterminate form, this limit of the ratio between derivatives may not be an indeterminate form. So in that case, we can calculate the limit. And of course, we can replace the first condition by plus minus infinities. Okay. Okay, we will prove L'Hopital's rules later, but first, before that, we will study some examples, applications of the L'Hopital's rule. Example. Let's see. So now, finally, we prove this formula. Okay, to prove this, first we see if all the conditions of L'Hopital's rule are met. Okay, first of all, sine x and x are differentiable. On all of real numbers, which, this is an open interval. So that is good. And first, we have the limit of sine x when x approaches 0, and that is 0. And limit of x when x approaches 0 is, of course, 0. So the first condition is met. And the second condition, the derivative of x is 1, which is not 0 for all x for all real numbers. So the second condition is okay. And the third condition, let's see. Okay, sine x over x, so they are derivatives. So sine x, its derivative is cosine x, and the derivative of x is 1. So this converges to 1 as x approaches 0. Right? Cosine 0 is 1. So this limit does exist. So therefore, the limit of sine x over x does exist, and that is equal to cosine x over 1, which is 1. So now we have proved this formula. As a next example, consider this limit. X approaches 0 and log of cos of x over x squared. Now, cosine x should be positive, so we should really consider this x as pretty small, so that it's close enough so that cosine x is positive, because inside logarithm should be positive, right? So anyway, let's consider the limit of the numerator. And that is what? cosine 0 is 1 and log 1 is 0, so it should be 0. And limit x approaches 0, x squared is of course 0. So the first condition is okay. And the second condition, if as long as x is not 0, exactly 0, then the limit of x squared prime, so that's derivative of x squared, is x squared is oh wait a minute, it's not limit, just x squared prime, and that's 2x, and which is not 0 as long as x is not 0. So the second condition is okay. And the third condition, the limit, okay, so log cos of x prime. So the derivative of this function using the chain rule should be 1 over cosine x over negative sine x. Okay, so the limit of log cos x prime and x squared prime is limit of, let's see, negative sine x over cosine x times 1 over 2x. And let's see, so that is let's see, so we have sine x over x here, so negative 1 over 2 and 1 over cosine x. So this can be written as cosine x times sine x over x. Okay, so this part converges to 1 and this part converges to 1. So the limit of a product is the product of the limits. So this is 1 times 1. So that should be negative 1/2. So that's the limit. The next corollary is yet another version of L'Hopital's rule. And L'Hopital version 3. So again, we have f of x and g of x as differentiable functions. On this interval, b to infinity. And we have the following conditions. In this case, we have limits when x goes to infinity. And limit of g when x goes to infinity, they are both 0. And 2, for all x greater than b, we have g prime of x non-zero. And 3, this limit, f prime over g prime, x goes to infinity, this limit exists. Then we have this limit, f over g, this exists, and this limit is equal to the limit of the ratio f prime over g prime. And again, we can also include the cases where f of x and g of x they both diverges to positive or negative infinities. Okay, and of course this can be the same L'Hopital's rule can be applied to the case where the functions are defined on this interval from negative infinity to some finite value. In this case, we can take limit x going to negative infinity, and the same result holds. Let's see an example. Consider this limit. Limit x to infinity and x to the power of 1 over x. Okay, so let's define f of x as x to the power of x 1 over x. So we have log of f of x is 1 over x times log x. Okay, and first, if we take the limit x going to infinity log of x, this diverges to infinity. And the limit x going to infinity of x is also infinity. And second condition, x prime is 1, which is not 0. Okay, and the third condition, this limit x going to infinity log of x is derivative, and derivative of x that is 1 over x. So this is the derivative of log of x, and the derivative of x is just 1. So we have just 1 over x, and x goes to infinity, so this converges to 0. So therefore, we have the limit x going to infinity log of f of x. So this is given as this limit, which is 0. So now note this relation. F of x is equal to exponential of log of f of x. Okay, because logarithm is the inverse function of the exponential function, so we have this identity. And also, this exponential function is continuous. Okay, so we have limit x going to infinity x to the power of 1 over x. That is limit of, let's see, that is exponential of log f of x. So that is exponential of the limit of log f of x is 0. So that is e to the power of 0. That is 1. Okay, finally we want to prove L'Hopital's rule, but before that we need one theorem, which is called Cauchy's mean value theorem. So that is Cauchy's mean value theorem. So that's this. Let f of x and g of x be functions that are continuous on the closed interval a, b. and at the same time differentiable on the open interval AB. And also we assume that for all x in the open interval, g prime of x is non-zero. Then there exists a value c in the open interval such that f prime of c over g prime of c is equal to f of b minus f of a over g of b minus g of a. Okay, so this is a kind of extension of the mean value theorem we have introduced before. In other words, the previous mean value theorem is a special case of this Cauchy's mean value theorem, where the function g of x was just x. And just if you replace this to here and here, then you get the previous version of the mean value theorem. So let's prove this. First of all, this function g of x, by itself, it satisfies the condition of the mean value theorem. So it is continuous on this closed interval and differentiable on this open interval. So there exists some value d in the open interval such that g prime of d is equal to g of b minus g of a over b minus a. And by assumption, g prime of d is non-zero. So therefore, this numerator is not zero. G of b minus g of a is not zero. It's not implies therefore. So we can divide by this quantity, right? So let's define a new function h of x by f of x minus f of b minus f of a over g of b minus g of a, and times g of x. Okay, we can divide by this because of this, because it's not zero. It's guaranteed. And obviously, this function is continuous on the closed interval a, b, and differentiable on the open interval a and b, because this is just a linear combination of functions f and g. So this it is continuous and differentiable on these intervals. And moreover, let's calculate the value of h of a. So that is f of a minus b f of a over g of b minus g of a times g of a. So if you calculate this, let's see, f a gb minus f a ga minus, we have this f b ga f a ga over gb minus ga. Let's see, this is cancelled by this. We have f of a, g of b, f of b, g of a. And also calculate h of b. So that is f of b GB, GA, and GB. So that will be, let's see, FBGB minus FBGA minus FBGB plus FAGB and GB minus GA. And this is cancelled by this, so we have, let's see, FA GB minus FB GA, GB GA. And if you compare the two values, this one and this one, they are equal. So this is equal to h of a. Okay, so the values at a and b are the same for this function h. So we can apply Rolle's theorem. There exists a value c in the interval a, b such that h prime of c is equal to 0. Right? So for this value of x, c, we have h prime c is equal to f of c minus f of b minus f of a over g of b minus g of a times g of g prime of c. So that is equal to 0. So since by assumption g prime of c is non-zero, therefore we have f prime of c over g prime of c equals to f of b minus f of a over g of b minus g of a. And the proof is done. Now let's prove L'Hopital's rule version 1. So let's review first the conditions on which this rule applies. So we have two functions, f of x and g of x, which are differentiable. On the open interval a, b. Okay, and we have a few conditions. Limit a to x to a from the right. So this is a right limit. This is equal to the limit x approaching a from the right. That is both 0. Okay, and for all x in the interval, we have g prime derivative of g being non-zero. And 3, the right limit, x to a from the right, and f prime over g prime exists. So if these three conditions are met on differentiable functions f and g, then we want to prove that this right limit f of x over g of x exists, and that is equal to this right limit f prime over g prime. So this is the limit. which we want to prove now. Okay. Now, for convenience, let f of a equals to g of a equals to 0. This is just for convenience. No, in the original conditions, these functions are defined only on this open interval, so a is not included. But now, since we define the values at a to be just 0, these functions are defined on this semi-closed interval from a to b, including a. Okay, and now by condition 1, f and g are continuous. Continuous on this interval, a to b, including a. Okay, and so for any x within a and b, between a and b, now f of x and g of x are continuous on a to x, including x. Okay, and also differentiable on this open interval between a and x. Okay, so now also by condition 2, for all t between a and x, g prime of g prime of t is non-zero. So we can apply, therefore we can apply Cauchy's mean value theorem. But before applying this theorem, we have to check the conditions for which this theorem is based, on which this theorem is based. So that is, if we apply this theorem, there exists some value, let's call it cx, within this interval between a and x, such that f prime cx over g prime cx is equal to f x minus fa over gx minus ga. But by definition, the values of f and g at a, they are both 0. So this is just a ratio between f of x and g of x. And obviously, as x approaches a from the right, this value of cx approaches a from the right, as x approaches a from the right. Okay, and by condition 3, this limit, if x approaches a from the right, f prime c of x and g prime c of x, this exists, right? Because if x approaches a from the right, cx approaches a from the right. And by condition 3, this ratio must converge. Okay, therefore, let's see. So because this limit exists, that means but this ratio is equal to this ratio, right? So therefore, this limit x approaches a from the right, fx over gx exists. And that is equal to, and is equal to this. So this is the ratio between f prime and g prime at cx. But as x approaches a, cx approaches a, right? So it's the same limit as f prime of x and g prime of x as x approaches a from the right. So that was to be proved, and the proof is done. Next, let's prove the case when the limits of f and g are positive or negative infinities. This is plus minus infinity, and the limit of g is also, the right limit is plus minus infinity. Okay, first, okay, proof for when these are true. Then let's see, let's define this constant L as the limit of the ratio of derivatives. Okay, so this limit exists due to the condition 3. Okay, so in terms of epsilon delta argument, this means this: for any epsilon that is positive and real, there exists some delta, let's call it delta 1, that is positive and real, such that if x is between a and a plus delta 1, then this difference f prime over g prime minus L is less than epsilon. Okay, so this simply states this fact. Okay, so it's just based on the definition of limits. Okay, so now from these given conditions, we have x approaching a from the right, f of x, let's say g of x, yeah, is plus minus infinity. So this means there exists some delta 2 positive and real, such that if x is between a and a plus delta 2, then g of x is greater than 1. Okay, so this 1 could be any positive real number, but for convenience, we choose 1 in particular. Okay. Now, let's define delta prime as the smaller of delta 1 and delta 2. Okay, and define, for convenience, define d as a plus delta prime. So now we apply Cauchy's mean value theorem. So by Cauchy's mean value theorem, we have for all x between a and d, so d is a plus delta prime, there exists some value cx within, let's see, for all x there exists some cx uh, wait a minute, x and d such that, okay, such that f prime of cx over g prime of cx equal f of d minus f of x and g of d minus g of x. Okay, so if we divide both numerator and denominator by let's see, let's divide it by g of x and f of d. So g of x, okay, both g of x, f of d and g of x, and that is 1 minus g of d over g of x. Okay, now by rearranging this a little bit, we have f prime cx over g prime cx equals to f of x over g of x minus r of x, where this new function r of x is defined as f of d g of x, wait a minute, where is it, and f prime of cx and g prime of cx times g d and gx. So if you just substitute this rx to here and do some calculation, you should recover this expression. Now you should note that cx, f prime of cx and g prime of cx appear on the both sides. Okay, so here, left hand side and right hand side. On the right hand side as part of this r of x. Now let's look at this expression more carefully. And first of all, by condition 3, this one, this left hand side converges to a finite value. Okay, and in this r of x, f of d is a finite value. Okay, and g of d is also a finite value. And g of x, it will diverge to infinity or negative infinity as x approaches a from the right. Okay, so that means as a whole, this r of x converges to 0 as x approaches a from the right. Okay, so the left hand side converges to a finite value, and on the right hand side this r of x converges to 0. So that means the remaining part, f of x over g of x, that should converge to the same value as the left hand side. So let's formally state these facts. So first, this r of x converges to 0. So that means for any epsilon that is positive and real, there exists some positive and real number, let's call it delta 3, such that if x is between a and a plus delta 3, then r of x is less than epsilon. I mean, r of x modulus is less than epsilon. So this means r of x converges to 0 as x approaches a from the right. Okay, now let delta be the minimum of delta 3 and delta prime. Delta prime appeared before. So this means f of x over g of x minus L. So L is the limit value of this one. Okay, and this is equal to, wait a minute, f prime of cx and g prime of cx minus L plus rx. So this equation comes from this equation, right? So if x is between a and a plus delta, then the absolute value of f over g minus L is less than or equal to, by using the triangle inequality, we have cx g prime of cx minus L plus r of x. Okay, so this is less than 2 epsilon. Okay, so this is less than epsilon and this is less than epsilon. So overall, the entire expression is less than 2 epsilon. But this epsilon can be any positive real number. So that means this ratio f of x over g of x converges to L as x approaches a from the right. Okay, so that was to be proved, and we are done. And I will skip the proof of for the case where we take the limit of x going to infinity or negative infinity. So in that case, if we just replace the variable like t equal to 1 over x, then the proof should be reduced to the previous cases where the limit is taken to 0. Next, we explain Taylor's theorem, which is actually one of the most important theorems in calculus, in entire calculus, I would say. The essence of differentiation is approximating any function by a linear function. But we can extend this argument to include higher order differentiations and to approximate any functions by polynomials of higher degrees. So here's the theorem. It's called Taylor's theorem. Okay, so let f of x be a function that is of the class Cn. So that means n times differentiable and continuous, and on open interval. Okay, then for all x in this interval, there exists Cx between a and x. A and x. Oh, wait a minute. And let a is a point in this interval. Okay. So we say Cx is between a and x because x can be greater than a or less than a, or maybe equal to a. So to include all those cases, we just say this is between a and x. Okay, so such that f of x is equal to f of a plus f prime a x minus a plus 1 over 2 f double prime a x minus a squared plus and so on, and n minus 1 factorial. This is n minus 1th derivative at a, and x minus a to the power of n minus 1 plus 1 over n factorial, and this is nth order derivative evaluated at cx actually, and x minus a to the power of n. So now look at the left hand side, right hand side. So f of a, this is a constant. F prime of a is a constant, and f double prime of a there is a constant. And actually, all these differential coefficients are constants. Okay, and x minus a, it's a linear function of x, and x minus a squared is a quadratic function of x, and x minus a to the power of n minus 1 is a polynomial function of a with a degree of n minus 1, and of course this is a polynomial function of x. So this function can be approximated by a polynomial function like this. So if we choose a appropriate value of cx, we can approximate any function as long as it's Cn. So let's prove this. Okay, so first of all, if x is equal to a, then this is just trivial, right? So if you just substitute x equal to a, then everything in this polynomial part will be 0. So that is just equal to, the left hand side is equal to f of a. So it's trivial. So we could just set cx equal to a. And suppose, so this case is done, so suppose b is not a. And wait a minute. First of all, we have to assume that b is in this interval, and b is not equal to a. And what we need to show is this equation with x replaced by b. So f of b is equal to f of a plus f prime of a, b minus a, and so on. Let's see, n minus 1, n minus 1, b minus a to the power of n minus 1 plus there should be some constant, let's call it cb, cb, and b minus a to the power of n. So we need to show this. For some cb, that is between some cb between a and b. Okay, so for that, let's define a constant a by this b minus a to the power of n is equal to f of b minus f of a, f prime of a, b minus a, and so on, plus n minus 1 factorial f, so n minus 1 derivative and b minus a n minus 1, and that's it. So basically, we subtract the left hand side, the right hand side, except for the last term, except for this term, okay, from the left hand side, and to define this constant a. This is a constant. B, this is a constant. Everything is a constant on the right hand side. And then define a function g of x by f of b minus f of x plus this and f of minus 1 x and b minus x to the power of n minus 1 and plus a times b minus b minus x to the power of n. Okay, now this polynomial g of x is differentiable function on interval I, and due to the way we define this constant a, we have g of a is equal to g of b, which is equal to 0. Right? So if you just substitute x equal to a, and this should be 0, right? Because this constant a is defined in this way. So if you just substitute all x by a, it will be 0. And also, if you substitute x with b, it should be also 0. These polynomial parts will be all 0, and f of b will cancel this f of b. Okay, so now we can apply Rolle's theorem. So that means there exists some value, let's call it CB, between A and B, such that G prime of CB is equal to 0. So let's calculate the derivative of g of x. And g of x is, so we have f of x here, so we have f. This is a constant, so it will disappear. And let's see. It will be f prime of x plus f prime of x. So this one, wait a minute. So from this one, we have f prime of x. And from this one, by using the differentiation of a product of two functions, we have f double prime and this one. So if we differentiate this part, it will be negative 1 times f prime. Okay, so with this negative sign, we have positive this one, f prime. Okay, and from differentiating this part, we have, let's see, we have minus f double prime of x and b minus x. And now we have the third polynomial of we have a polynomial of the second degree. Okay, so we have f double prime x, so that's 1 over 2 f double prime of x and b minus x squared. It's somewhere here. So if you differentiate it, differentiate this part, it will be b minus x and negative 1, and this 2 will be cancelled by this 2. So it will be this b minus x. So this will cancel, and if you continue this, everything will cancel. And after some calculation, what's left is this. From the last few terms, we have nth order derivative b minus x to the power of n minus 1 plus na and b minus x to the power of n minus 1. Okay. So the last term appears from here, and this term comes from this part, and we differentiate this part and leave this part untouched. Okay, so that's this one. And if that the part we get by differentiating this part will be cancelled by some previous terms. Okay, so that's what we have at the end. And since we have this, so g prime of cb is equal to 0. So if you substitute x with cb, we have 0 equals to n minus 1 factorial f n times derivative cb. Wait a minute. Is it cb? Yeah. cb and b minus cb to the power of n minus 1 and plus na b minus cb to the power of n minus 1. Okay, so we can solve this for a, and let's see. This part will be cancelled, and divide by n, we have n factorial, and a is equal to 1 over n factorial and nth derivative of f evaluated at cb. So that's the value of a. So if we substitute this a into g of a equals to 0, then so this here we have the equation to be proved. So that is what is it? This equation. Okay, so after all, this was a. Okay, so and if we substitute x with a, and the value is 0 here, so this becomes 0, and this becomes wait a minute, 1 over n factorial and nth derivative of f evaluated at cb So all the x's are replaced with a. So that, and put everything on this side to the left, and we have fb equals to this. And that is the equation to be proved here. Now let's consider the meaning of the Taylor expansion. Okay, so let's see. Given some function f, let's define a polynomial function by this. So pk of x is a polynomial function. F of a, f prime of a times x minus a, and 1 over 2 f double prime a of x minus a squared, plus and so on. And we take up to kth order derivative. And this is a kth order polynomial. Okay, so we define this way, and let's take the difference. Now consider pk minus 1. So this is the polynomial of k minus 1th order. Okay, so consider this, and the difference between f of x and the polynomial pk minus 1 of x is this. I think I should write n minus 1 here. So that will be n factorial and f n a x minus a to the power of n. Okay. So when n is sufficiently large, when n is large, so sufficiently large, and x is sufficiently close to a, so that means x minus a is small. So small means, no, we don't specify any specific value, but small means less than 1 or less than 0.1 or less than 0.001 and so on. Okay, and if this is the case, then this difference is very small, because it is x minus a, which is already a very small number, and we take that to the nth power. So that's very small. Okay, consider x minus 1. For example, if x minus a is something like 0.1, and consider n is like 100, then this value is very small, whatever this value is, as long as this is constant. Okay, this is finite. Okay, we're assuming this function f of x is at least of Cn class, right? So that means nth derivative is still finite. It converges, and yeah, so it's finite value. So if x minus a is very small, then this should be very small. So that means the difference between this function and the polynomial defined by this is extremely small. So this means we can approximate any function of class Cn by a polynomial function. Okay, pretty well. Let's see some example. Okay, consider f of x equal to sine x. Okay, and let's say a is 0. So we evaluate all of the derivatives at 0. Then we have the first polynomial is x. So So that is defined, just apply the definition of this polynomial. So that's f of 0 plus f prime of 0 evaluated at 0. Okay, so this is the first polynomial, and sine 0 is 0, and derivative of sine is cosine, and if we evaluate at 0, that is 1, so that is just x. Okay, and for p2, we can evaluate the derivative at second derivative at 0, but that is just 0, so that is actually same as p1, because this is 0. Okay, so this is not meaningful. And p3, so we add, so that's p1 plus third derivative evaluated at 0. So that is okay, we also divide by 3 factorial of 3. So that is actually x minus 1 over 6 x cubed. And p4 is the same as p3 because the fourth of the derivative is just 0 if we evaluate at 0. So that's not meaningful. And p5 is, if we continue the same procedure, this will be 1 over 120 and x to the power of 5. Okay, so if we plot these functions, then we get this. So this purple line is the sine function. So that's this. Okay, then p1 is just a straight line, this one. So this is a kind of approximation we get by a linear function. So this approximation is good as long as we are somewhere very close to x equal to 0. See, if we expand this here, it's almost like straight line. So this is a good approximation as long as x is very close to 0. Okay, but the difference between the approximation and the real value becomes very large as we go away from 0, right? So the difference between here and here is, it's becoming larger and larger. Okay, then approximate by p3, that is a cubic function. So that's this blue line, blue curve. So this is better than the straight line. So let's look at somewhere here. So where, let's see, this is around x equal to 1, the difference between the real value and the straight line is non-negligible, but the difference between the real value and the cubic polynomial, we cannot see from this picture. It's pretty good. But still, if we go away from 0 farther and farther, then the difference becomes apparent. Okay, so like this, larger and larger. Now let's look at p5, which is the yellow line. This one, it's gold line. So now this approximation is a lot better than the cubic line. So the difference between the real value and the approximate value is a lot smaller at larger larger values of x, right, compared to the straight line or the cubic curve. The difference is very small. So if we increase the order of polynomial, like p7, p9, and so on, the approximation becomes better and better. So in this way, we can approximate any well-behaved functions to an arbitrary precision. And these polynomials are, expansion is called a Taylor expansion of functions. Let's define some terminology regarding the Taylor expansion. So first of all, this expansion is called, and this expression is called the finite Taylor expansion. And the last term, this one, is called the remainder or residual. Okay, remainder or residual of the Taylor expansion. Okay, and also when, in particular, when a is equal to 0 in this expansion, we call it, instead of Taylor expansion, some people call it Finite Maclaurin expansion. Okay, it's just a special case of Taylor expansion. Okay. And also we could have written this one. Instead of Cx, we could have written something like, so Cx could be written as a plus theta x minus a, where theta is between 0 and 1. Maybe inclusive. Let's see a few examples. And the first is very famous, and you should be very familiar with this expression. So exponential of x can be written as this: 1 plus x squared over 2 plus x cubed over 3 factorial, and so on. And x to the power of n minus 1, n minus 1 factorial, and x to the power of, let's see, I should write e to the power of theta x and x to the power of n over n factorial. And this theta is somewhere between 0 and 1. So this is a Maclaurin expansion around Taylor expansion around x equal to 0, or Maclaurin expansion of the exponential function. And another example is log x plus 1. So this is x minus 1 over 2 x squared plus 1 over 3 x cubed minus 1 over 4 x to the power of 4, and so on. And in general, we have negative 1 to the power of n minus 1 factorial, x to the power of n minus 1, and so on. This one, and n theta x plus 1 to the power of n. And theta is between 0 and 1. So this is the Maclaurin expansion of log x plus 1. It's not log of x, it's log of x plus 1. Okay? So you should try to derive these expansions. Next, we define a new notation, which is of great convenience. So that's called Landau's O. Landau's asymptotic notation. Asymptotic notation. So let's see. Let's say we have f of x and g of x defined in the neighbor of a. So defined in the neighbor of x equal to a. So this means it's defined on some interval which includes this point. Okay. Then if we have this limit f over g, if this limit is 0, then we write f of x is O of g of x as x approaches a. Okay, so this is called little o. Meaning f of x converges to 0 faster than g of x converges to something, okay, so to speak. So this means f of x has a lower order of some kind than g of x. This is called little o notation. Okay. For example, if f of x is little o of 1, so what this means is this: limit of f of x over 1, which is limit of f of x, is 0. Okay. So as x approaches to some value, just say a in this case, if f of x is little o of 1, this means f of x approaches 0 faster than 1 approaches 0, which never approaches 0, of course. So this means f of x converges to 0. Okay. And second example, if we write f of x is equal to 2x squared plus o, little o of x squared as x approaches 0, this means there is some function h of x such that f of x can be written as 2x squared plus h of x, and the limit as x approaches 0, h of x over x squared is 0. Okay, so this means the contribution of h of x is very small compared to the contribution of x squared. Okay, so that we can effectively ignore this term. So f of x behaves much like this function plus something, but which is negligible. Another simple example would be like this: x squared is little o of x. Why? As x approaches 0. Okay, this is because x squared over x is x, which approaches 0 when x approaches 0, right? So therefore this holds. Now we have the language to describe the next theorem, which is about asymptotic expansion. Okay, and let f of x be a Cn function defined on some open interval containing a. Then we have f of x equals to f of a plus f prime of a x minus a and f double prime of a 2 x minus a squared and so on, and nth derivative f factorial n minus a to the power of n plus little o of x minus a to the power of n as x approaches a. Okay, so this is called asymptotic expansion of f of x. Okay, and let's prove this. But the proof of this seems almost trivial, since we already have Taylor's theorem. But anyway, let's do it. So for simplicity, we consider the case where a is equal to 0. So we consider only Maclaurin expansion. Okay. So if that's the case, we have f of x equals to f of 0 plus f prime of 0 x f double prime of 0 over 2 x squared and so on, and f to the power of n factorial and x to the power of n plus some function g of x where g of x is defined as this 0 n factorial, and wait a minute, since it's a remainder it should be theta x and x to the power of n minus this last term and evaluated at 0 and x to the power of n. Okay, so just factorize them. We have theta x minus 0 over n factorial x to the power of n. Okay, and we know from the given condition, c f of x is of Cn class. So this function, nth derivative, is continuous, okay, because of this. So this means this numerator, let's say, since fn of x is continuous. So therefore, fn theta x minus fn 0 converges to 0 as x approaches 0. Right? Because if x approaches 0, then this theta x approaches 0. So they should be equal, because it's continuous. So therefore, g of x, that is this, g of x over x to the power of n converges to 0. Right? So if we divide this by x to the power of n, this will disappear, and the remaining part is this, which converges to 0. So that means, therefore, g of x is little o of x to the power of n as x approaches 0. So that was to be proved, and we are done. We use this little o notation when we are interested in some qualitative behavior of a function rather than quantitative behavior. For example, let's see, suppose we have this function x squared, 2x squared, and 2x squared plus 3x cubed or 2x squared minus 4x to the power of 4 and so on. Strictly speaking, these functions are different from each other. And when x is large, like 100 or 1000, these terms, cubic terms and quartic terms, they have significant impact on the behavior of these functions. So all these three functions behave very differently. However, when x is very small, indeed when it's approaching 0, then these higher order terms becomes increasingly unimportant compared to these quadratic terms. So compared to 2x squared, these terms, cubic or quartic terms, they become negligibly small. So that's why we express these terms as little o x squared to express the fact that they have a negligible impact on the behavior of these functions. So in this way, we can discuss all these functions all together without being distracted by the details of the behaviors due to higher order terms. Next, let us see some of the basic properties of little o notation, and that is summarized as a lemma. Okay, as x approaches 0, we have the following. First, x to the power of m times little o x to the power of n is equal to little o x to the power of m plus n. And also, second, little o x to the power of m times little o x to the power of n is equal to little o x to the power of m plus n. And third, little o x to the power of m plus little o x to the power of n is equal to little o x to the power of l, where L is the minimum of m and n. Okay, so let's prove this. First one and the second one are mostly the same, so I'll just prove the first one. So we divide this one by x to the power of m plus n. But this will cancel, so we have little o x to the power of n over x to the power of n, which converges to 0 as x approaches 0. Now this is the definition of little o notation, so it's done. And similar for the second one. And for the third one, let's say L, we assume, without losing generality, we can assume that m is less than or equal to n. Okay, then and then L is equal to m, because that's the smaller of m and n is m in this case. Okay, if opposite is true, then we just set L equal to n, so it's not a problem. So we divide little o xm plus little o xn over little x to the power of, in this case, m. Okay, so this can be split into the sum, and x to the power of n minus m times little o x to the power of n over x to the power of n. Now, since m is less than or equal to n, this is positive. N minus m is positive or 0. Anyway, as x approaches 0, this will converge to 0, and by the definition of little o, this converges to 0, and this converges to 0. So everything converges to 0. So therefore, we have this result. Okay. So basically, if we add anything that is higher order than some specific power, then we don't have to worry about the additions of those powers. Now let's see an example, and we try to find the fourth order asymptotic expansion of this function x plus x squared times exponential of x at x equal to 0. So we have this Maclaurin expansion of exponential function x plus 1 plus x plus 1 half x squared and 1 over 6 x cubed and 1 over 24 x to the power of 4 plus little o x to the power of 4. And let's see. So we take the first 1, 2, 3 terms and x plus x squared and all x squared. So if we multiply both sides by x squared, we have x squared, x cubed, 1 over 2x to the power of 4. And this one, the last term, will be little o x to the power of 4. Okay, and we add this and this. So both are fourth order polynomial. Then we have, so the left hand side becomes 1 plus x squared times e to the power of x. And let's see. So 1 plus x plus this x squared will be 3 over 2x squared. X cubed will be 7 over 6x cubed. And this x to the power of 4 becomes, should be what? 13 over 24 x to the power of 4 plus little o x to the power of 4. Okay, so this this little o, if we add them, we still have this little o x of x to the power of 4. As another example, we give an alternative proof of the sine x over x when x approaches 0. Its limit is 1 using an asymptotic expansion. First of all, sine x, if we expand this, the first term will be x, and the rest is little o of x. Actually, the next term in the Taylor expansion will be x cubed times some constant. So, but anyway, it's still little o x. So this limit, sine x over x when x approaches 0, is limit x plus little o of x over x. And so this is 1 plus little o x over x. So this is 1 plus limit little o x over x. But this is by definition converges to 0, so this is just 1. But effectively, this is, what we are doing here is just applying the L'Hopital's rule indirectly. After all, this expansion comes from the derivative of sine x. This is the first derivative. So Yeah, so it's the same thing, almost. So that's all we are going to study about differential calculus, at least for now. And from the next chapter, we study integral calculus.